screen. Okay, share screen. Okay, share screen. Can you join it?
Hello?
Yeah.
Okay. Hello?
Yeah, madam.
Okay.
I can stop the video. The trouble is Hi, am I audible?
Yes, you are.
Okay. And you were able to see my screen as well, right?
Yes, we could.
This one. Okay. Thank you.
Sunil, we can't see your screen. It was visible.
Yes.
It was visible a few minutes.
I stopped.
Okay.
I stopped the screen sharing because otherwise I can't see the participants. So I'll start it here.
Yeah.
Start the video.
Hello, Sunil.
Hi, Nitin. Maybe we'll wait for a couple of more minutes. So we have 26 participants. Yeah, maybe 2 minutes. Okay, let's start. We welcome you to the 40th edition of FSTTCS. We were supposed to be. Yeah, I hope now you can see the slides, I guess, right?
Yes.
Okay, so we welcome you to the 40th edition of FSTTCS. We were supposed to be here. Unfortunately, that did not materialize, hopefully next year. So I'll just make a few brief comments about the structure of the schedule. The detailed schedule is available on the conference website. So the main conference is for 3 days, 15, 16, and 17.
Sunil, the slide is still not full screen. Yeah, it is
Oh, I
quite
see.
small.
Okay, okay, 1 second.
Maybe you need to do some full screen.
Is it better now? Is it fine now? Is it fine now?
Yes, yeah, great. Okay, now it's full screen.
Okay, so yeah, so the main conference is for 3 days, and every day we have 2 invited talks and 2 sessions of contributed talks. On 15th and 16th, that's today and tomorrow, we start with an invited talk, followed by 2 sessions of contributed talks, and we end with an invited talk. On 17th, we start with 2 sessions of contributed talks, followed by 2 invited talks. There's also this discussion session, which is clearly marked in the program. These are unstructured sessions, so we hope that this will facilitate discussion among the participants. So in total, we have 27 contributed talks in track A and 25 in track B. So we have four of our invited speakers are located in the US, 3 along the Pacific coast. So that's the main reason behind this this non-standard scheduling. So we apologize for the inconvenience it might cause to some of our participants. We have a workshop in programming languages, which is running in parallel with the main conference. We have a post-conference workshop on advances in verification, which is scheduled on 18th. We already had 2 pre-conference workshops, one on metrics rigidity and the other one on uncertainty in games, which were held on Sunday and Monday. So thanks to the very efficient staff at Lipix, the proceedings of the conference was published about a week back. It's available as volume 182. And we also have a conference YouTube channel where the pre-recorded videos of all the contributed sessions are uploaded. And we'll be doing live streaming as well. These videos are organized as playlists corresponding to each session, so it should be easy to identify. We have a virtual space organized on gather.town. This is to facilitate the discussion among the participants. And we also have a Slack channel, which the authors might find useful if they have technical issues. There will be a technical support team always available on the Slack channel. So details of the proceedings and the conference YouTube channels are available on the FSTTCS website. The details about gather.town and the Slack channel, we had sent a mail to all the registered participants. All this has been made possible thanks to the hard work of the organizing committee. We are indebted to the organizing committee for getting the conference running. So all the protocols that you see in place, these are basically efforts of the organizing committee. We thank the speakers for submitting their papers. Thanks to their timely responses, we have the pre-recorded videos of all the contributed talks on the conference YouTube channel. We thank the invited speakers for readily accepting our invitation and being very flexible and accommodative to all our requests. We thank the workshop organizers for organizing these interesting workshops, covering a wide range of topics which are significant to the FSTTCS community. We are grateful to the program committee members for helping us design this very interesting program. Thanks to their efficiency, we were able to stick to the initially announced timeline in spite of postponing the paper submission deadline. We are thankful to the FSTTCS steering committee for pretty much giving us a free hand in taking many of the crucial decisions in terms of the structure of the conference. And finally, we thank all the participants for joining us today, in spite of the difficulty with the differences in time zones. So if anyone has questions about the structure of the schedule or the conference, we'll be happy to answer them. Thank you. Okay. Hi, Joël. So I think you will be able to share screen now, right? Maybe you can try.
Yeah. There we go. How is that?
It's good. Okay, so it's 2 o'clock. Let's start. It's my pleasure to introduce Joël Ouaknine, our first invited speaker. Joël graduated from McGill and Oxford, and subsequently he was a professor of computer science at Oxford. In 2016, he moved to Saarbrücken on a very prestigious research position. And currently he is a scientific director at the Max Planck Institute of Software Systems in Saarbrücken, where he also heads the group Foundations of Algorithmic Verification. Joël is an expert in the theory of formal verification. He has made fundamental contributions to time systems and infinite state probabilistic systems. More recently, he and his co-authors have made significant contributions to the theory of linear dynamic systems. These are systems where transformations between states are specified by linear transformations, and it's a topic which has profound connections to many other areas in mathematics, like number theory. Joël has received various awards and recognitions for his work, including the Roger Needham Award for Young Computer Scientists, and more recently the Saloma Prize for his work in the theory of time systems and analysis of dynamical systems. He's also the recipient of the prestigious ERC Consolidator Grant. And today, Joël will tell us more about holonomic techniques, periods, and decision problems. Joël.
Thank you very much, Sunil. Thank you for this very kind introduction, and thanks to the organizers for inviting me. It's a pleasure to speak at this. It's a real pleasure to speak at this conference. I also would have wished, for it to be in person in Goa. I guess. I think we're seeing the light at the end of the tunnel is sort of what I'm hoping. That's the important thing. So here we are. So I'll speak today about holonomic techniques. If you have never heard of these things, then that's great, because I'll try to explain what they are from the ground up. And I will, so there'll be a part of the talk based on, existing work and then some new results in the sort of second half of the talk. I should say that much of this work is joint with colleagues. So some of them, so they're listed here. Some of them are in my group, postdocs, and also my colleague James Joël, who's at Oxford, with whom I've got a long-standing collaboration, and then some other people, including some people as far as South Africa. Florian Lucke is a mathematician in South Africa. So let me start. So, oops, there we go. Okay, so I will start with a quote by Don Knuth, where Knuth says, "Science is what we understand well enough to explain to a computer, and art is everything else we do." And you may or may not agree with this. I mean, perhaps it's a little bit sweeping, but certainly in the context of holonomic techniques, and as far as from my point of view, more generally in theoretical computer science, this quote resonates with certainly a lot of what I'm trying to do. So, kind of trying to make things systematic that otherwise we know how to do, but in a sort of ad hoc fashion. So. Start with the question, what do all of these things have in common? I've got a bunch of items here. I'm not going to read them all. You just sort of let you cast your eye over the list that I have here. I should say this list has been shamelessly stolen from a presentation of Cyril Banderier. And the question is, what do all these things that seems like a very heterogeneous list of things, what do they all have in common? And the answer is they all depend at some level or other on holonomic techniques. So let me try to, so you can see that holonomic techniques are quite pervasive. And let me now try to explain, how these things work. And by the way, I'm not monitoring the chat or questions, but if there are questions, then I guess the host, Sunil or somebody should feel free to interrupt me. I'm happy to take questions in real time. So let me start with a simple example. Let's say, suppose you're asked to prove this binomial, this identity, right? That involves a sum of square of binomial coefficients. So this is n choose k squared. And you want to prove that this is 2n choose n. Okay, suppose you're asked to do this. So one way to prove this, I'm just going to give you an elementary proof. So on the right-hand side, you have the number of ways to choose n letters amongst 2n letters. So suppose you've got the 2n letters a1 up to an, and b1 up to bn, and amongst these 2n letters, you want to choose n. Well, the number of ways there are to do this is obviously 2n choose n. Now, another way in which you can choose n letters amongst 2n letters is you can choose k letters amongst the a's, and n minus k letters amongst the b's. So you have n letters in total. And of course, there are n choose k ways to choose k letters amongst the a's, and n choose n minus k ways to choose n minus k letters amongst the b's. And so therefore, the total number of ways there to do this, you take the product of these things. And now, of course, you must sum over all possible values of k. And now you have all possible ways to select n letters amongst 2n letters. So therefore, the two things have to be equal. So if we take this the sum now, we've got the summation of n choose k times n choose n minus k. But of course, n choose n minus k is equal to n choose k by the symmetry of the representation. So that's really the sum of n choose k squared. And as we've just argued, this is equal to the right-hand side, which is 2n choose n. And I think Knuth would say this is art. This is a cute little proof. It's nothing super deep, but it's cute, it's beautiful, it's nice, but it's art in a sense that it is not obvious that this is systematic, this generalizes. If I change this 2 into a 3 or something, it's not at all obvious this, these kind of tricks could work. Let's see how we could have done these things in a systematic way instead. So I do apologize. Sometimes I'm going to take a different approach, reproving the same identity. So here I have a number here on the left-hand side that depends on n. For every value of n, this gives you a different number. So I'm going to call this the sequence of the numbers that you get in this way, un, the sequence un. And on the right-hand side, of course, I also have a sequence of numbers that I'm going to call vn. And the high-level strategy, so I want to show that un is equal to vn for all n. And the high-level strategy is that I'm going to try to find a recurrence relation for the sequence un a recurrence relation for the sequence Vn. I'm going to combine this to obtain a recurrence relation for sequence Un minus Vn. And I'm going to verify that Un minus Vn is identically 0 by checking a finite number of initial values. And once I've done this, I will know by induction that Un minus Vn is identically 0, or in other words, that Un is identically equal to Vn, or in other words, that this equality here really is an identity. Okay, so let's see how this works. So let's start with the right-hand side. So I'm writing Vn as 2n choose n, which is 2n factorial over n factorial squared. And 2n plus 2 choose n plus 1 is given by this expression here, which is given by, I expand it and I get this expression. And you can see now the term Vn appears because I've got 2n factorial, I've got n factorial, and I've got n factorial. And so I get a recurrence relation here. Vn, so n plus 1 squared times Vn plus 1 is 2n plus 2 times 2n plus 1 times Vn. And now you can see that every term here, Vn plus 1, depends only on one previous term. So we say we have an order 1 recurrence relation, and therefore I have to give one initial condition, which is that V0 by inspection is equal to 1. And that's it. My equation, the equation I have here entirely specifies the entire sequence of numbers Vn. So I can do the same thing for the left-hand side. So I let Un be the summation of n choose k squared. And now if I try to express Un plus 1 in terms of Un, or Un plus 1 in terms of Un and Un minus 1, it's kind of not obvious what to do, right? This is kind of a little bit tricky. But it turns out that the summand here, n choose k squared, is so-called sister-Celine summable. And I will come back to this notion later. So just for the time being, just take my word for it. And it therefore turns out that there is an algorithm you can use to compute a recurrence relation for the sum of these UNs called Zeilberger's algorithm. And if you invoke Zeilberger's algorithm, and again, I will come back to this a bit later, you automatically derive the recurrence n plus 1 times Un plus 1 is equal to 4n plus u times Un. So again, you have an order 1 recurrence. You have to specify the first value. So by inspection, you plug in n equals 0 there, and you get u0 equals 1. So in other words, if we look at our identity again, we have a recurrence relation for the left-hand side for the UNs, a recurrence relation for the VNs. Okay. So both UN and VN satisfy a so-called holonomic recurrence relation. That is a linear recurrence relation with polynomial coefficients. But I will give a formal definition shortly. Of order 1, meaning that every term depends only on one previous term. Now, therefore, the sequence of the differences, so the sequence of UN minus VN, will satisfy a holonomic recurrence relation of order 2. Okay, so this is by fairly straightforward application of linear algebra. And therefore, if you know that UN minus Vn satisfies a recurrence relation of order 2, you don't even need to calculate it, although you could if you wanted to, but you don't even have to. You only need to verify that the first two values, U0 minus V0 and U1 minus V1, are 0. Because now by induction, because UN plus the third term in the series will be a linear combination of the previous two, but if the previous two are 0, the third term will be 0, and by induction every term will be 0. So you conclude that UN is identically equal to Vn, and you have concluded your proof. And this is something that can be made completely systematic, and this will become more clear as I go on. Let me show you a slightly more complicated example to show you that this is not just kind of a little theoretical toy. So in 77, Roger Apéry produced what was described as a sensational proof of the irrationality of zeta of 3. This is the Riemann zeta function evaluated at the integer 3. And sort of mathematically, it's given by this expression, by definition. And the critical ingredient in Apéry's proof are the definition of these Apéry numbers. So these Apéry numbers here, it's a slightly more complicated sort of binomial, sum of binomial coefficients, sum of squares of binomial coefficients, well, product of squares. And Apéry claimed that these numbers, okay, which are given here for every n, these numbers obey a second order holonomic recurrence. So here you have a cubic polynomial times an plus 2, okay, an are my numbers, minus another cubic polynomial times an plus 1, plus a third cubic polynomial times an equals 0. So now you can see that an plus 2 implicitly now depends on an plus 1 and an. So that's why it's order 2, because you depend on 2 previous term. And the thing is, Apéry was, when he presented his proof, he sort of presented his result, but didn't actually prove the recurrences that he'd found. And he was asked about, well, how do you know this holds? And he said, where did you find these identities? And his answer was cryptic. He said, oh, they grow in my garden. But of course, number theorists wanted to prove that this sequence of numbers really does obey this recurrence. This is not at all obvious. And van der Poorten, who's a very well-known number theorist, together with Henri Cohen, tried to another number theorist, tried to prove it. And van der Poorten writes, neither Cohen nor I had been able to prove the above in intervening 2 months before the International Congress of Mathematicians, in which Apéry was to present his proof. After days of fruitless effort, the specific problem was mentioned to Don Zagier, and with irritating speed, he showed that indeed the sequence satisfies the recurrence. This more or less broke the dam, and the rest of the proof was quickly conquered. But it's interesting that 2 very strong number theorists were stuck on proving that these numbers here, the sequence of numbers here, obeys this holonomic recurrence. Now, it turns out that poor van der Poorten was a couple decades too early, because if he'd asked this question, a couple of decades later, he could have used Zalberger's algorithm instead of using Don Zagier, not only to prove the recurrence, but even to derive the recurrence from scratch. So here's a picture of Doron Zalberger with a fitting t-shirt. And if you implement Zalberger's algorithm, which it is implemented in, there are various packages and Maple packages, Mathematica packages. So in the sum tools package in Maple, you have the sum recursion command, and here you put in the expression for the Apéry numbers, and Maple will automatically spit out the recurrence that we had on the previous page in slightly different notation. So this is actually remarkable, because Maple not only proves this, because the algorithm is correct, but can even give you a certificate, but in fact can even derive these recurrences automatically in the kind of the shortest recurrence. So this I find, I don't know how you feel, but I find this absolutely remarkable. Let me give you a third example. Now this time about continuous function, because the point about holonomic techniques is that they apply to discrete functions and also to continuous functions. So suppose you're asked to prove the following trigonometric identity. So sine of 2x is 2 sine x cos x. Now you may ask, well, what am I allowed to, if you want to prove something like this, what exactly are you allowed to assume? So what we're going to assume are the differential equations that define sine and cosine, along with the initial condition. So the second derivative of sine x is minus sine x, second derivative of cos x is minus cos x, and then you have the initial conditions for sine and cos. Okay, and it's a second order linear differential equation, so you need 2 initial conditions, and likewise for cos. And that's it. We're only going to assume this. And the strategy will be similar. We're going to label the left-hand side f of x, and the right-hand side g of x. So f and g are now continuous real-valued function, and we want to show that f of x minus g of x is identically 0. Now, if you look at the left-hand side, you you see that f obeys a differential equation, and that's completely immediate from using just the chain rule and using the differential equation for sine. And so in other words, f of x satisfies a second-order linear differential equation. Now, if you look at g of x, it is the product of 2 functions, each of which satisfies a second-order linear differential equation. Now, again, by linear algebra, from completely general, just a simple linear algebra argument, you can conclude that g of x will itself satisfy a linear differential equation of order at most 4. Okay, so g of x has order at most 4. And therefore, the difference, f of x minus g of x, again, by linear algebra, I'm not showing details, but just take my words for it, f of x minus g of x, because f of x satisfies an order 2 ODE and g of x an order 4 ODE. So h of x, the difference between the two, will satisfy an ODE of order at most 6, which you can compute. And now you can verify that h of 0 is h prime of 0, h double prime of 0, etc., all the way up to the 5th derivative, and they're all 0. And this you get simply from what's in the box here. It's completely straightforward. And now you can invoke the Picard-Lindelof theorem. Basically, the point is now that all the derivatives are, the value of the function at 0 is 0, and all its derivatives, its first 5 derivatives are 0, and satisfies the node of order at most 6, and therefore, and by uniqueness of the Picard-Lindelof theorem, you know there's a unique solution, and the 0 function satisfies this ODE and these initial conditions, and therefore h of x has to be that function, identically 0. In other words, f of x is identically equal to g of x. And this was done, I think you can see this was done completely systematically. I mean, there was nothing special about, you know, sign and so on. I could put any other trigonometric identity and basically the same technique would apply. Okay, so let me try to define these things a little bit more formally and then state these results also a little bit more formally, the kind of theorems that you have. So a sequence of real numbers, a sequence UN of real numbers is so-called holonomic, also known as p-finite or p-recursive, you might find in literature, if it satisfies a linear recurrence relation with polynomial coefficients. So you have polynomials p0 up to pk. So these are single variable polynomials with coefficients in rational coefficients, such that the following recurrence holds. So pk of n times u sub n plus k is here, you can see it's a linear combination of the previous values of un, so un plus k minus 1 all the way up to un, with the coefficient, with the multiplied by the polynomials applied at n. So p sub k minus 1 of n times u sub n plus k minus 1, etc., all the way up to p0 of n times un. Okay, whenever you have a sequence of numbers that obey such a relation, it is by definition holonomic. And example of holonomic sequences abound. So the factorial numbers, the Fibonacci numbers, harmonic numbers, Perrin numbers, Motzkin, Catalan, Aperi numbers, etc. These are all holonomic sequences. The sequence of numbers form holonomic sequences. Also, the Taylor coefficients of many, many functions. And this is not a coincidence. We'll come back to this later. But just to give you a quick example, if you take the function sine x and its Taylor expansion is x minus x cubed over 3 factorial plus x5 over 5 factorial, etc. And therefore, the sequence of coefficient, well, for the even degree values of x, you have the coefficient is 0, but then the coefficients alternate. So you have 1 minus 1 over 3 factorial plus 1 over 5 factorial, etc. So you can quickly verify that the relation that the coefficients obey is n plus 2 times n plus 1 sub un plus 2 is minus un. And with the initial conditions 0 and 1 for the sequence. Okay, now, in fact, according to Manuel Cowers, approximately a quarter of the sequences in the OEIS are actually holonomic. But of course, not all sequences, are holonomic. Here are some non-examples in case you're wondering. So 2 to 2 to the n, log n, the Bernoulli sequence of Bernoulli numbers, the prime numbers, these are all provably non-holonomic sequences. Holonomic sequences have some very nice closure properties. So if un and vn are holonomic sequences, then you can add them, you can pointwise multiply them, you can shift them, you can take the sequence of partial sums, and you can take the Cauchy product of the two sequences. This is the product you would get if you were multiplying two power series. And these closure properties make it a very nice class for computer algebra, obviously. And I should stress that all these operations are completely effective in the sense that if you give me the recurrence for un and the recurrence for vn, then mechanically I can obtain the recurrence relation for all these objects. Now, of course, if you want to talk about algorithms, a holonomic sequence is an infinite object because it's an infinite sequence of numbers. So you have to manipulate it in a finitary way, but of course you can, because you only need to provide a description of a holonomic sequence, you only need to provide the description of the recurrence relation together with finitely many initial values of the sequence. And now the result, the main result in terms of algorithmics is that if you're given two holonomic sequences, un and vn, in this sort of way, and the initial values belong to some ring in which you can make comparisons. Here I'm writing the algebraic numbers. Then the equality problem is a sequence un identical to sequence vn. That is a decidable problem. Okay, so the identity problem. So the slogan is identity is decidable for holonomic sequences. Okay, so let's talk about holonomic functions. So a function, now f is a function from some interval, so interval of the reals into the reals. A function f is holonomic or d-finite, d stands for differentially finite, if it satisfies now this time a linear differential equation with polynomial coefficient. So you have the polynomials like before, polynomials in one variable with rational coefficients, such that the following relation holds. So p0 of x times f of x plus p1 of x times f prime of x plus dot 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 plus pk of x times the kth derivative of f of x is equal to 0. And examples of holonomic functions are all algebraic functions, sin x, e to the x, log x, Bessel functions, hypergeometric functions, Hankel functions, Airy functions, polylogarithms, elliptic integrals, what have you. There are many of them. In fact, according again to Cowers, approximately 60% of the functions in this handbook of mathematical functions are actually holonomic. They also, as you might imagine, enjoy very nice closure properties. So if the class of holonomic functions, so if f and g are holonomic functions, then you can add them, multiply them, perform integration, differentiate, and also compose with an algebraic function. So if a is an algebraic function and f is holonomic, then f of a of x, the function you get from the resulting composition, is also holonomic, not in the other direction, but in this direction, yes. And once again, all these operations are completely effective in the sense that if you give me the differential equations for f and g, I can compute algorithmically the differential equation for each of these things on the left-hand side. Okay, so now in terms of algorithms, so what you have is the following. So let I be an interval of the reals, and let's assume without loss of generality that this interval contains 0. If it doesn't, you would have to perform a shift the function. Now, to define a holonomic function from this interval to R, you need only provide the differential equation together with finitely many initial values at 0. So f of 0, f prime of 0, f double prime of 0, etc. And there's a side condition that says, provided that 0 is not a root of the polynomial coefficient of the highest order term of the differential equation. So that's so that the Picard-Lindelof theorem will apply. Well, of course, polynomials have only finitely many roots. So if 0 is a root of that polynomial, then just shift a little bit and then find another point at which the polynomial doesn't have a root. So this can always be done without loss of generality. And now the main result is that given two holonomic functions f and g from I to R with initial values in some ring in which you can make comparisons, so let's say the rational numbers or the real algebraic numbers, the equality problem is f identically equal to g as a function is decidable. So the slogan again is that equality or identity of functions is decidable for holonomic functions. And now we come to what I call the fundamental theorem of holonomy theory. Now, nobody else calls it that. I'm hoping to start a trend. I really think it should be called the fundamental theorem of holonomy theory. And by the way, I should say, I was once asked, oh, is this your result? And I should say all of what I'm talking about is classical. So none of these things are my results. So the theorem says that basically there is this correspondence between discrete holonomic sequences and continuous holonomic functions, both ways. So let un be a holonomic sequence, and now let's form the generating function of the uns. So this is the function you get by forming the following power series. So f of x is the sum of un times x to the n. That function, that object viewed as a function, is a holonomic function. And conversely, the sequence of coefficients of the Taylor expansion of any holonomic function is always holonomic as a sequence. And moreover, these transformations are fully effective. Okay, so we'll come back. We'll use this result later on. We'll come back to it, and we'll come back to this result. But just as a quick example, if you take everybody's favorite recurrent sequence, holonomic sequence, or C-finite sequence, a Fibonacci sequence, so the sequence going 0, 1, 1, 2, 3, 5, etc., and you form the generating function, so the sum of fn x to the n, you get the following rational function, x over 1 minus x squared. This of course is a holonomic function because it satisfies an order 1 differential equation. That's a one-line sort of derivation. Okay, so let me talk a little bit about the history of these holonomic techniques. Where do they come from? So if you consider the absolute simplest holonomic sequence you can have, that would be given by a recurrence of the form b times un plus 1 is a times un. Okay, that's the simplest, that's not completely trivial. And the nth term of the sequence will be given by the expression a over b to the n times u0. So it's going to be a geometric progression or a geometric sequence. Now, suppose you replace the constants a and b by polynomial. So instead of having b un plus 1 equals a times un, you have b of n times un plus 1 equals a of n times un, where b of n and a of n are polynomials in n. Now, you don't get a geometric sequence, you get a hypergeometric sequence. These are the so-called hypergeometric sequences, and the corresponding power series, if you form the power series, they are the hypergeometric functions. Okay, and they have this standard notation for hypergeometric functions. And these are all holonomic, of course, but they're a subclass of all holonomic sequence, but they're already an important subclass because they include the exponential function, logarithmic, trigonometric, many trigonometric functions, binomial, Bessel function, and a bunch of other very classical functions. And the study of these things originated with Wallis in the 17th century. And then there was extensive work by Euler, especially by Gauss, Kummer, Riemann, Ramanujan, and contemporary mathematicians such as Boykers and Zudelin. And nowadays, this is a major research area in its own right in number theory. So the study of hypergeometric sequences and functions is completely, it's completely a major research area. Now, of course, hypergeometric sequences are first-order holonomic sequences. Every term in a sequence depends only on the previous one with this, with these two polynomials, the relation given by these two polynomials. But of course, you can ask, well, what about arbitrary order holonomic sequences? And these were systematically studied by Poincaré in the late 19th century. And Poincaré's interest in these things was to focus on the asymptotics. How do the asymptotics work? And there were many other people, of course, that followed, including Perron, Coman, Bruno Salvi, Philippe Flageolet, who's depicted here. Many results. And lots of progress. But in terms of algorithmics, and now speaking as computer scientists, I guess algorithms is one of central concern of ours. The paradigm shift or the revolution really occurred with the advent of this woman, Mary Celine Fasenmeyer's PhD thesis in 1945. So this woman was a Catholic nun from Pennsylvania. And whilst being a nun, she wrote a PhD thesis at the University of Michigan, in which she developed an algorithmic method to find recurrence relation satisfied by sums of terms of hypergeometric sequences. And this is now known as Sister Celine's method. And in fact, the very first example of this talk was a textbook example of the kind of sequences that can be handled with Sister Celine's method. Unfortunately, so she wrote this PhD thesis, and then she published a couple of papers, and she left mathematics, unfortunately, and went back to being a nun, I guess, doing her nunly duties. But her work didn't die. It was picked up by others, including Gosper, Richard Stanley, Gessel, Lipschitz, and in particular, it was weaponized by Zeilberger in a seminal 1990 paper called A Holonomic Systems Approach to Special Function Identities. And in that paper, Zeilberger elaborates the theory of multivariable holonomic system based on Bernstein's deep theory of D modules from differential algebra. So what Zeilberger does is he considers not just single variable holonomic sequences and functions, but multivariable such, in which you can have some continuous variables, some discrete variables, and he shows these just completely astounding identities amongst these, these functions. He has algorithms to compute identities for these things. And a couple of years later, in 1995, he wrote a book with two co-authors, Pitt-Kosek and Wilf, in which he explained his algorithms, but specialized just for the special class of hypergeometric sequences and functions. But even for that class, it was, this work is completely remarkable. In fact, Don Knuth wrote the foreword, and Knuth says, I fell in love with these procedures as soon as I learned them because they worked for me immediately. Not only did they dispose of sums that I'd wrestled with long and hard in the past, they also knocked off two new problems that I was working on at the time I first tried them. The success rate was astonishing. this book will help you reach new frontiers. So I think this is really high praise, coming from Knuth, arguably is, the master of these kind of combinatorial identities. Now, this is all wonderful, but of course, holonomic techniques, so you can do a lot with them, of course, but they also have limitations. And in the sort of second part of the talk, starting now, I want to talk a little bit about the limitations and some of the progress. And the limitations have to do with the fact that everything that I've talked about up to now has been about proving identities, proving equalities. But what has been not nearly studied as much is how do you decide inequalities, or how do you, what about asymptotics, right? What if you're interested in, the rate at which a particular function or sequence will grow, etc. So I will just to make things a bit more concrete, let me just introduce 3 problems that are kind of algorithmic problems that are I think very interesting. So the first one, hypergeometric inequality. So here you're given UN and VN, 2 hypergeometric sequences, and you ask, is it the case that for every n, UN is bigger or equal to VN? Okay, so this is a very natural question. I mean, we know how to check that UN is identically equal to VN, but what if you want to know whether UN is greater or equal to VN? You could think of this problem as, maybe UN is counting, some kind of how many objects, combinatorial objects of a particular type there are, and VN of another type, and you want to make sure that there are always more objects of the first type than of the second type, or something like this, right? Anyway, I think it's a very natural problem. The second problem is the positivity problem. So here you're given a holonomic sequence, UN, and you want to know, is it the case that all the numbers in the sequence are non-negative? And the third problem is the minimality problem. So you're given, again, a holonomic sequence, and you ask, is it minimal? Now, I have not defined minimal. I will shortly. But just to fix, just to get a picture, a mental picture, if you don't know what it means, you can say, well, suppose you want to decide, does UN tend to 0 as n tend to infinity? Okay, suppose that UN is a sequence of rational numbers. I mean, this is a very, very natural question, right? Asymptotically, do you tend to 0 or not? And now I will just sort of, give away a little bit. If you ask, these problems, what's their complexity and so on, well, we don't even know that these problems are decidable, any of these problems. We do have partial results, but it's actually remarkable that these problems, none of these 3 problems are actually known to be decidable at the time of, that I'm speaking. So these problems, I think you will agree, have a different flavor from the problems before. So earlier we're looking at equalities and identities, and this has a very algebraic flavor. And now we're looking at inequalities and asymptotics, and that has a very analytic flavor. And there's, I think, an interesting anecdote by the French mathematician David Mador on algebra versus analysis. So here's what David Mador writes. He says, I was once dining at the IHES, it must have been in '96, and I happened to be seated right next to I.M. Gelfand, who's pictured here. When I said I wanted to become a mathematician, he asked whether I preferred algebra or analysis, and I said algebra. I don't understand why people want to study algebra, replied Gelfand, because in algebra, you write A equals B, but if A equals B, then A and B are the same thing. So you're writing A equals A, and what's the point of that? Well, I'm not as smart as Gelfand, so I wrote my PhD in algebraic geometry anyway. I like this this anecdote, and there's there's probably a little bit of truth to what is being said. I mean, it's actually also funny that the famous book of Zalberger and co-authors is actually titled A equals B. Okay, so let me introduce a subject here. Let's consider the Fibonacci recurrence equation, which I think everybody knows. So it's xn plus 2 equals xn plus 1 plus xn. Now, there is a very famous solution to this, the sequence 0, 1, 1, etc. But in fact, any sequence that satisfies this equation is a solution of the recurrence. So if you start with any 2 numbers, x0 and x1, let's say -9 and +7, then you will get a sequence through this relation, and that will be a solution of the Fibonacci recurrence. And the set of all such solutions forms a 2-dimensional vector space. And that is very obvious, because if you take 2 solutions of Fibonacci and you add them, then you can, it's very easy to verify that again you have a solution. And if you take solution of Fibonacci and you multiply it by constant, again, you have a solution. So it is the set of solution forms a vector space. Moreover, it's two-dimensional because you have 2 degrees of freedom, right? Once you select the first 2 values, x0 and x1, the entire sequence is fully determined. Now I can define minimality, and this is fully general. This doesn't just pertain to Fibonacci. So a non-zero solution UN is minimal if for any other linearly independent solution Vn, we have that the ratio of UN over Vn tends to 0 as n tends to infinity. Okay, so you notice the only thing I need here is linear independent. So I need to know that solutions form a vector space, which they always do. This is the case in general for holonomic sequences. And a sequence is minimal if you take any other linearly independent solution and UN over Vn tends to 0 when n tends to infinity. When that happens, the sequence is minimal. Let's see what that means in the case of Fibonacci. So if you take the Fibonacci recurrence, we know that any solution to the Fibonacci recurrence can be written as a times phi to the n plus b times phi bar to the n, where phi is a golden ratio and phi bar is the Galois conjugate of the golden ratio, and a and b are 2 arbitrary real numbers. And now if we look at this, well, the golden ratio has absolute value greater than 1. So if a is non-zero, this term here, a times phi to the n, this term will tend to plus or minus infinity. Whereas a phi bar has absolute value strictly less than 1. So no matter what b is, this term will always tend to 0 as n tends to infinity. So now we can see very clearly what the minimal solutions are. Any sequence UN in which a is 0 is a minimal solution. Okay, so they will actually form a vector space themselves, the sequence of minimal solutions. And they're exactly the ones where a is equal to 0. Okay, so let's view this in with a picture. So here's the vector space of Fibonacci sequences of solutions of a Fibonacci recurrence. So here this is R squared, and I want you to think of every point here in R squared corresponds to a sequence. Okay, so for instance, the classical Fibonacci sequence 0, 1, 1, 2, 3, 5 is the point here in red because the first 2 values are 0 and 1. So I've put this point at coordinate 0, 1, okay, U0 and U1. And that uniquely defines the entire sequence. Okay, so every point here corresponds to what I call a Fibonacci sequence. And phi bar numerically is here, as value here. And now the set of minimal solutions are all the sequences that lie on this blue line. Okay, so you take any point on this blue line, that the corresponding sequence is a minimal sequence. And you can see that in particular, the sequence that begins 1, phi bar is a minimal solution, right? Because it's on this blue line. Now, a very important concept is the critical ratio, which we call mu, which is the slope of this line. And because you see the point about this line is that the ratio of the first 2 values of the sequences on this line is always the same. It's always phi bar. So whether you're minimal or not as a Fibonacci sequence is whether the ratio of your first 2 terms is equal to U1 over U0 is equal to phi bar or not. Okay. So let's see this in a slightly different way. I'm now going to plot UN against N. So on the horizontal axis, I've got N. And here I'm going to plot UN, where UN is a solution is a Fibonacci. It's going to be a Fibonacci sequence. So suppose I start with the first 2 values, U0, U1, 1, phi bar. So I've said this was a minimal solution. And what happens? I have 1, then phi bar, then some other value. And you can see as n tends to infinity, the value of UN tends to 0, in fact, pretty quickly, as unsurprisingly. What if instead of starting with 1, phi bar, I start with 1, phi bar plus a tiny amount? Okay, so here I'm just a little bit about phi bar. Then what happens is, well, as you might expect, initially I sort of mimic the minimal solution, but around 15 or so, n equals 15, I start diverging to plus infinity. And what if I were to start with 1, and then a number that's slightly below phi bar? And then, as you might expect, I sort of mimic the first 2 sequences for a while, and then I diverge to minus infinity. And you can see that if you take the ratio of the first 2 terms, when the ratio is phi bar, then I'm exactly minimal. When the ratio is above phi bar, then I go to plus infinity. And when the ratio is below phi bar, I go to minus infinity. Okay, so you can kind of understand now this minimal sequence, this critical ratio business, because if you're above the blue line, the ratio of the first two terms is bigger than 5 bar, and you will go to plus infinity. If you're below the blue line, you will go to minus infinity, and on the blue line, the ratio of the first two terms is exactly 5 bar, and you will tend to 0. Let me talk about the a priori numbers again as another example here. So this is the holonomic recurrence relation we had for the a priori numbers. If you remember them, we had them earlier in the talk. Now, the a priori numbers, numerically, the sequence of numbers is actually the sequence, numerically it begins with 1, 5, and afterwards you could compute the sequence of numbers simply from this relation, right? So, because it's a second order holonomic relation. Now, another solution to the a priori recurrence begins with 0, 6. And now you actually have not necessarily integers, but rational numbers. And that's because you have to get xn plus 2, you have to divide by some numbers. This is how you get rational rather than integers, but it's a perfectly valid sequence. And now, of course, any linear combination of an and bn is going to be a solution to this recurrence, right? Because they form a vector space. So in particular, un defined to be bn minus zeta of 3 times an is a solution. And the punchline of a priori's proof is the fact that un tends to 0 fast as n tends to infinity, which shows that zeta of 3 cannot be rational, because if zeta of 3 were a rational number, it would be approximable by rational numbers too well. And therefore, it cannot be a rational number. Okay, this is completely elementary number theory, but this is basically the punchline. But from our perspective, what is interesting is that the sequence un is a minimal solution, okay, from the fact that it tends to 0. In fact, just from the fact that it tends to 0, it follows that it's a minimal solution. And therefore, you may ask, well, what is the critical ratio? What is the mu for the a priori sequence? Well, it's the ratio of the first two terms of the sequence un. And you can plug it in. So the first two terms of un, it involves zeta of 3. And you can see that the critical ratio, if you just calculate, it's a number that depends on, involves zeta of 3. So it's kind of interesting, because now you have a recurrence, but the critical ratio involves something as weird as zeta of 3, right? The Riemann zeta function evaluated at 3. So this is kind of, earlier we had the golden ratio, the conjugate of the golden ratio. Now we've got zeta of 3. And suppose that you want to know, I give you another sequence, is it minimal? Well, it will be minimal if and only if the ratio of the first two terms is equal to this mu. But how do you compare, if I give you a rational number or an algebraic number, how do you compare it with something that depends on zeta of 3? We know zeta of 3 is irrational, but we don't even know if it's algebraic. Okay, so it brings us to questions of comparing real numbers to know whether a sequence is minimal or not. And in general, this is, as we know as computer scientists, we know this is a difficult task. So here's a funny, interesting little example. Suppose I ask you, is this real number here on the left-hand side equal to square root of pi? And you might wonder, and you might say, well, I don't know. You might try to evaluate it numerically, and you find that actually the two sides agree to over 42 billion digits. Okay, that's how close they are together, but they're not equal. And I stole this example from this entertaining paper, Strange Theories and High Precision Fraud by the Borwein brothers. But the point is that comparing real numbers is in general something that cannot be expected to be done. But there is a class of numbers for which it is at least conjectured that you can compare them, and that's the class of periods that come from algebraic geometry and number theory. So these were introduced by Kontsevich and Zagier. Here's Don Zagier, and Kontsevich was his PhD student, who then went on to earn the Fields Medal in '98. And in 2001, they defined a period to be a complex number whose real and imaginary parts are values of integrals of algebraic function over semi-algebraic domains. So you have an integral over a semi-algebraic domain D, and G, it's an integral of a function G, which is algebraic. Okay, if you don't exactly know what these things are, just don't worry. This is not going to be critical. But just to give you an example, So periods include all algebraic numbers. So because any algebraic number, like let's say cube root of 7, well, you can just write it as an integral. This is a period just by definition. But they include a lot more numbers than that. So pi, for instance, is a period. Log 2 is a period. And even our old friend zeta of 3 is also, as it happens, a period. Now, periods, in fact, they go back to Grothendieck. Here's the definition of, sorry, this is in fact, Grothendieck did not formally define periods, but he formulated conjectures about periods. And here's the Grothendieck period conjecture. I'm not going to read it, but I encourage you, if you, I guess you'd have to go back to the slides, but it is, to my mind, just truly incomprehensible. I mean, this is very, very deep. And I have the greatest respect for people working on this. I mean, as you can see, it involves the RAM cohomology and rational homology and all kinds of very complicated stuff that I don't understand. But the good thing is that an equivalent conjecture was formulated by Kontsevich and Zagier that I find easier to understand. And that conjecture is, it is decidable whether two given periods are equal or not. And there are various results, in fact, very recent results on progress towards proving this conjecture. So there are special cases in which this conjecture is known to hold. Now, this can also be generalized to the notion of exponential period and also pseudo period. So I'm not going to go into these the technical details of how to define these things, but okay, but I will come back to them. But the important thing is that we're going to assume that periods have a decidable equality problem, or at least certainly this is a conjecture that we will assume. So let me now take you through an example of how you might try to decide positivity or minimality for a holonomic sequence. And here I'm going to give you the simplest non-trivial example that I could come up with. So this is it's a second order sequence. So second order because every term of the sequence depends on a previous two. And it's a holonomic sequence, but the polynomials are as simple as possible. They're all linear polynomials, okay? You've got 2n plus 3 xn, 6n plus 7 xn minus 1, 4n plus 1 xn minus 2. And suppose you're given such a sequence and you're given the first two values. So here I start, instead of starting 0 at u0, u1, I started minus 1, 0. This is because that's how the paper is written and the calculations are done with this. This obviously doesn't matter. So, but we start u minus 1, u0, and then u1, u2, u3. So suppose I give you the first two values, and let's say the rational numbers or real algebraic numbers. And I want to decide whether the corresponding full sequence that obeys this recurrence is a minimal sequence, or whether it's a positive sequence. Every term is non-negative. How would I go about this? Okay, so let me just sketch at a high level how the proof works. What are some of the key ingredients? And here's how it goes. So the first thing you do is for every n, you consider the characteristic polynomial of the corresponding recurrence. And this is a polynomial in Z here. That's the polynomial. And you compute the roots of that polynomial, which you denote little lambda n and big lambda n. And then you can show, and this is all very straightforward, that the little lambda n tend to a real value, which is 1, little lambda, which is 1, and the big lambda n tend to big lambda, which is 2. And now there's a classical result due to Poincaré and Perron that tells you if you have any solution un to this recurrence, then the ratio of consecutive terms, un over un minus 1, the ratio of consecutive terms of a sequence either will tend to little lambda or to big lambda. Okay, so this is a theorem. This would be true of the Fibonacci sequence, for instance. The ratio of consecutive terms will tend either to the golden ratio or to the conjugate of the golden ratio. And now you can see, well, if the ratio of consecutive terms tend to 1, then the terms are not growing very fast. And those are the minimal sequences. But if the ratio of consecutive terms tend to big lambda, which is 2, then they're growing fast, and those are not obviously the minimal sequences. Okay, so un is minimal if and only if the ratio of consecutive terms tend to 1. Okay, so just take my word for this. This is also specific to that particular example. Sometimes the roots are complex conjugates, sometimes the roots are repeated. Here I've taken a simple example. The two roots are 1 and 2. Okay, so now what is the critical ratio? Well, if we rewrite the recurrence in this way, all I've done is I've divided by 2n plus 3. It turns out that the critical ratio is given by Pinkerel's theorem as this infinite continued fraction. This is the notation for an infinite continued fraction. I've written the first few terms here. So this is an infinite continued fraction in which I involve, this coefficient, and then I take it over all n, and this coefficient taking over all n. And numerically, the critical ratio is a little bit above 1/2. And I have no idea if this number is irrational, rational, transcendental. I think, if you ask me, it's almost certainly transcendental, but this is something I absolutely don't know. It also turns out in this case, there is another description of this number, which doesn't help very much, but in terms of a ratio of two Gaussian hypergeometric functions. But in general, this is not always available. In general, you only have the infinite continued fraction representation, which is not that useful, because if you're given two numbers and you ask, is their ratio equal to this infinite continued fraction? So you want to know if the sequence is minimal or not. You have to decide this equality. You don't know how to check whether two numbers are equal to an infinite continued fraction. So I'm going to plot here the ratio of consecutive terms, un over un minus 1 against n. So n is here on the horizontal axis. And I want to plot un over un minus 1 on this graph. So here's mu, a little bit about 1/2. Here's little lambda, which is 1, and here's big lambda, which is 2. And if the ratio of consecutive terms starts on the critical ratio, then indeed, as we know, the ratio of consecutive terms will converge to little lambda, which is 1. Okay, so you get this blue line converging. And by the way, these graphs were made with Mathematica. So this is really what you observe in practice. If the ratio of consecutive terms is a little bit above mu, then you see you will overshoot big lambda, and you will then converge as expected. And if you're a little bit above mu, but not a bit closer, then you will converge, but it will take a little bit longer. What if you start below mu? Then you will go negative, then you will go positive, and you'll converge to big lambda. And if you start closer to mu, but still negative, you will go up then down. So negative, then you go up, and then you'll converge to big lambda. So as expected, every sequence, the ratio of consecutive term for every sequence will converge to 2, unless you started exactly on the critical ratio, unless the ratio of the first two term was exactly mu, in which case you will converge to little lambda. So these are the minimal sequences, okay? But now the question is, how do you decide if I give you two terms and I say, I want this, these are the first two terms of my sequence. So that defines the sequence uniquely. How do you know if it's equal to mu or not? Well, you don't know what mu is. You can only approximate mu. And if you differ from mu by 42 billion digits, say, you're going to be on that trajectory for a very long time before you realize that, oh, actually, I'm going up or I'm going down. And so, what do you do? And the idea is you borrow a trick from analysis, which was sort of immortalized by Erich Hecke as follows. He says, it is a fact that the precise knowledge of the behavior of an analytic function in the vicinity of its singular points is a source of arithmetic properties. So what is the idea? The idea is you form the generating function of the UN. Okay, so here I'm writing it u sub n minus 1, because remember I started u sub minus 1, but it's a generating function, okay? And the point is that if the ratio of consecutive terms of the UN tends to 1, then what will the radius of convergence of this function f be? It will actually be 1. But if the ratio of consecutive terms tends to 2, the radius of convergence will be 1/2. So we can determine whether we're on the minimal critical ratio or not, whether the radius of convergence of f is 1/2 or 1. Okay, so here's how it goes. So I form my generating function. By the fundamental theorem of Holonomic theory, it obeys a differential equation, which is given here. And I can solve this using standard techniques. And this is my solution this is the solution of my differential equation. So f of x, my generating function here, is the square root of 1 minus x times this integral of a function in y, an algebraic function in y dy, but the integral from 0 to x over two terms that depend on x. And now if you look, you can see that this function has a pole at x equals 1/2. Because when x equal to 1/2, this value is 0. But if the radius of convergence of f is supposed to be 1, then that 0 here has to be canceled by a 0 above. Otherwise, this will blow up to infinity as you approach 1/2. Well, this cannot cancel, because when x is close to 1/2, 1 minus square root of 1 minus 1/2 is square root of 1/2, which is not 0. So this integral would have to be 0. So in other words, the sequence is minimal if and only if this integral is 0. In fact, I've shown only one direction. The other direction is straightforward. And now if you look at this integral, well, it's an integral of an algebraic function, and therefore it's a period by definition. And if you believe Kontsevich-Zakir, you believe that you can check whether this is equal to 0 or not. Okay, so let me, just in the interest of time, you can also decide positivity in this way. And so in summary, so these are, okay, some of the results we have. You can reduce the positivity problem to the minimality problem, and you can reduce these questions to whether a period, or more generally an exponential period or pseudo period, is equal to 0. Okay, so let me just conclude with this. I think this is a vastly underexplored territory, the algorithmic treatment of the analytic properties of Holonomic systems. So by this, I mean the analytic treatment, the analytic properties are inequalities and asymptotics. And so as Don Knuth would say, this project, it tries to move, more of the art into science. Thank you very much.
Thanks, Joel. We can take some questions. So you can raise your hand on Zoom, then I can see it. I think co-hosts cannot raise their hands, so they can just ask the questions. Prabhat has a question.
Yeah, so like membership of 0, for example, in a sequence, in a holonomic sequence, is that known to be undecidable?
Whether a holonomic sequence has a 0.
Yeah.
Okay, so that's kind of the Skolem problem for holonomic sequences. Yeah. It's not known to be undecidable, so I don't know of any undecidability result. In general, this is a hard problem. Even for second-order sequences, I don't know how to do it. So this is a very interesting problem. As you probably know, for C-finite sequences, so for linear recurrent sequences with constant coefficient, this is a hard problem at order 5 already.
Okay, so is there any generalization like known better than holonomic, for which undecidability is obviously known?
There are some undecidability results, I believe, with some polynomial recursive sequences, recurrent sequences. So sequences in which the UNs are allowed to appear as a polynomial. I don't know exactly what the results are, but I believe there are some undecidability there, but not for holonomic sequences, at least as far as I'm aware.
Thank you.
More questions? You can also just ask in case I am missing the raised hands. Aishwarya has a question.
Yes, thanks, Joel, for the very nice talk. So do this, all the problems that you discussed, do these also apply to formal power series when you do not have a, like you can look at recurrences which are defined in that way when you have multiple variables and
I see, with multiple variables.
For example, some of these recurrences that you describe, for example, can some kind of weighted automata describe them? For example, if you have, if it is over reals, then again this equivalence is decidable and all. So so of course I don't know how to handle the integrals or differentials and so on, but there seems to be some connection. I don't know.
That's a good question. I think if you have more than one variable, first you have to, I guess one would have to formulate exactly, how you want to formulate the problems, right? Yeah, I guess let me answer your question by saying I agree that these are interesting questions, and I think they have been very little studied. In fact, this is acknowledged by several authors. So Cowers and Pale-Wine, various people have said, oh, look, there's lots of algorithms on for equalities. For inequalities, very little is known. So I think there are lots of interesting questions. And, I think people should study them because they're interesting. And in this trick of the mathematician Polya, in his book, How to Solve It, he advocated the trick of, if you're attacking a problem, try to find the simplest instance of the problem that you cannot solve, and then solve that. And I think this is a good idea, right? You take a problem, such as the one you were mentioning earlier, maybe has some connection with weighted automata, as you suggest, and so on, and try to find the simplest example of the problem you're looking at that you still cannot solve. Attack it, and I think almost invariably you'll find interesting things. So I think, yes, I think these are good problems to look at.
Thank you. Thank you.
You're welcome.
I think
Meena had a question.
Yeah. So thanks for this very nice talk. This stuff was very new to me. So this question which I have may be a bit stupid. You mentioned, so if U and V are holonomic sequences, then the difference is also a holonomic sequence, UN minus Vn.
Yes.
What if I were interested in somehow I'm visualizing these sequences as curves and I want the area between the curves. So it's not UN minus Vn, but the absolute value of UN minus Vn. Then what can we say about how this behaves?
Oh, that's a super interesting. I don't know. I don't know. Now, these things I think they're not necessarily very easy if there's a lot of back and forth, right? Because
exactly.
the crossing points, in general, even when you have constant coefficients, you can ask this question for C-finite sequences. So, and let's say you only have one, but you're interested in crossing above and below zero. So now you're saying, I'm interested in, unless this area defined in some way, in some meaningful way. In general, these crossing points are not going to be so simple. Yeah, it's a very good question. It's a very good question. Again, I think this is a great question. I think it shows that this is, an area where there's lots of interesting problems, right? It could well be that this is solvable. So I don't know.
Okay.
It's related to some things I know, but there's nothing sort of outright that I can say, at least without fear of making a mistake.
Okay. Yeah. Thank you.
Thank you.
More questions? Okay, I guess we can take more discussions on Gather. So Joël, you'll be able to join Gather? Or...
Yes, of course.
Okay, so I'll paste the URL on the chat for everyone.
Okay, so I'm going to
and
go in. Is it on the chat? I don't see it on the chat.
I will. I'm just pasting it. Yeah, I'm just sending it. Yeah.
Thank you.
Yes. So the URL is that's the URL, and I guess we can have more discussions on Gather. So the sessions. So now we'll have these parallel sessions for track A and track B. That starts in about 24 minutes. Yeah. Thank you.
Thank you very much. Bye.